Hello, let's have a look at how we can implement the equivalent of iteration in LMC assembly code. So in a nutshell, iteration is where we have some looping, where lines of code are being repeated. We're thinking for loops, while loops, do until loops. Now, in assembly, we just do this via branching still, but it can perform the equivalent of a high-level construct like a while loop. So here's a question we'll try and implement in LMC. We're going to ask the user to enter a number. We're going to keep asking them to re-enter until it is equal to 0. When it is equal to 0, output -10. And here's the equivalent code in OCR pseudocode. How are we going to put this into assembly code? Well, we're going to start by asking the user to enter a number, and we're going to keep repeating until it is equal to 0. Now, I picked 0 as a nice, easy starting example because we've got BRZ. And like I said a minute ago, there is no iteration construct in LMC. So instead, we just use branching, but we use it in a slightly different way. So if it is equal to 0, therefore we can jump to essentially the end of my loop. So let's use a label. And this isn't showing iteration just yet, but if I put a label further down in my code, at this point, we're going to eventually halt it. We do need to print -10, so actually let's do that now. We are going to halt it, but only after I print -10. How am I going to get -10 outputted? Well, I can load in the output maybe, and let me set an output via dat. I'm going to set -10 to be saved under the label output, a bit like a variable. After -10 gets loaded into the accumulator, I can then just output it so we can see -10 on the screen. Then we'll stop. So if I put it in RAM and I type in 0, we should get -10 outputted and it should finish. So that's part of our program, but we are missing the looping part of this. So if it's not equal to 0, we need to just continue in this execution, and we need to do some branching. But this time, because I want to do a loop, we're going to branch back on ourselves. So if I do a branch always, so it's always going to branch at this point, we can branch always to the start of this loop. And if I put a loop label above the operand here, this results in it repeating. Because we have a branch always, it's going to jump up to this first line and run this first line again. And it's going to keep running this first line until we type in 0, when it will jump to end and eventually finish. So if I put it in RAM, I type in different numbers each time, but they're not going to be 0. I keep asking until eventually I type in 0 and we get -10 output. Let's now have a look at an example which might require a for loop if it was in a high-level language, which is printing integers from 1 to 10 inclusive. My code looks pathetically easy to do when it's in a high-level language, but we know it's going to be a little bit harder in LMC. Okay, so it can be helpful to try and almost convert the procedural code literally in some cases. So that for loop, we had I as our variable. I started at 1, we outputted it, we added 1 to it, we then stopped when I got to 10. So it might help you just to almost set an I variable, which is initially 1, and use that in your program. We also need to set an endpoint here, which was 10. So I can do that at the start. When you're doing it on paper, you might want to leave these dat lines to the end because they should come right at the bottom of your program. But on my computer, obviously I can put it in there now. What's the first thing I need to do here? Well, there's no user input. I need to start by printing out 1, and that's what I is initially. So if I load 1 into the accumulator via I can then immediately output it, and we would get 1 output straight away. At which point I need to add 1 to this. So I need a 1 dat line as well. Don't forget that these are labels to memory addresses. So really that's saying in a memory address, which I'm calling 1, put the value 1. And at that point, it's tempting just to loop from this. We could add a label back to the top, and we could, just thinking to myself where that label goes. Let's put it right at the top. At that point, we can just loop it. The issue there is we're adding 1, but we're not actually saving it to I. So what I should have done after adding 1 is make sure I save it back to that label. So adding 1 to it, we're then saving it back, and so on and so on. If I run it here, we now get this numerical sequence. The The issue is I've not taken into account the end. So it's going to be an infinite loop here. It's not ever going to stop. I've not told it to stop. We've got a branch always. It's always going to loop. So how can I tell when my value of I reaches 10? There's no branch if equal to 10 opcode. So I've got to use what I've got available to me. And our tactic we've used before, in the last video in particular, is we are able to subtract 10 from I if the result is equal to 0, therefore I is equal to 10. That's kind of our trick for comparing in LMC. So how are we going to do this? Well, before we branch, we don't want to branch always at this point because we need to see whether it's equal to 10 or not. We're going to need to subtract 10 from the value of I. So if I go sub, I don't need to make another variable because I've got end already. If I subtract 10 from I, if this is equal to 0, therefore we're going to jump to the end. I've already used end as a label, so maybe let's call this halt. If it's equal to 0, we need to end. And we don't need to do anything at all. We just need to end our program. So if you're doing it on paper, you've got to check through this yourself. I can test it in a second, but it's worth just reading through your code and seeing if it makes sense so far. So we are outputting our value of I. We're adding 1 to it and saving it back to memory. We're then subtracting end, which is 10 from it. If it's 0, we're going to halt. If it's not, we're going to go back to the start. And despite me subtracting 10 from it, because I previously saved the value of I to memory, and then I load it back again, that shouldn't be an issue particularly. Now, an issue we have a lot in LMC is we often stop a little bit earlier. Maybe we are expecting. And that may happen here. Yes, it has happened here. So I've got 1 to 9, and actually I wanted 1 to 10. And this all relates to essentially my position of my output line. I'm outputting quite early on in this program, and I'm outputting before I'm doing all of this checking to see whether it's equal to 10 or not. So the issue is, if it is equal to 10 at that point, 10 is being saved to the I memory address, but then I'm never actually looping back round to output it, right? So, okay, we had 1, it's now equal to 10. We save 10 to the I location. We subtract 10 from it. Oh, we discover it's equal to 0 because it was 10. Therefore, we're halting straight away, and we never actually get to see the 10 in the output. So a couple of ways we could rejig this. We could, it adds a couple of lines here. We could load back in, oops, let's not do that. We could load back in I here and then output it before we halt it. So I'm kind of mopping up for one last print I need to do here to make sure we do get 10 actually shown to the user. So that's one way of doing it. I also think a slightly hacky way of doing it, which saves adding lines, is to make this 11 instead. So that it always goes 1 extra time than it should, but this does have the effect of not showing 11, but it does show 10 because of this slightly dodgy order. So either would be fine, and this isn't the only way of doing it. You could also move out to be a little bit further down potentially too. A few ways of solving that issue. You don't discover that issue if you actually bother to either run it on a computer, or if you're doing it in an exam situation, if you actually trace through it yourself. So if you have got time, do check your code carefully, because those edge cases often happen. You can't necessarily tell they happen until you've tried it yourself. Although I appreciate in an exam, it's a little bit tricky to do that. You don't always have the luxury of a few minutes to actually check your code carefully. Lastly, let's look at a slightly more applied example where it's not telling us to use a loop necessarily, but we can implement this using a loop in LMC. So we're asking the user to enter a first number, then we're going to ask them to enter a second number, and we're going to output the first number, div the second number. So performing quotient here, which is telling us how many whole times does the second number go into the first number. And because we don't have a div opcode in LMC, we've got to be a bit more ingenious and use a loop to try and implement this. So quotient or div or integer division, it's got a few different names, is performing division. We're just not counting any fractional parts. We always get rid of the point something which you might get from a division. So division is just repeated subtractions ultimately. So our approach here is going to be basically to count how many times we can subtract the second number from the first number, and that will give us the quotient. So we're going to need to get two sets of user input here. We're going to need to save these. It's always a good idea just to immediately save user inputs, especially if you have multiple, because if we put multiple imps back to back, they would overwrite each other. So you're never really going to cause us a difficulty if you save these as DATs. Now, of course, if you were doing this on paper, you would perhaps write these DAT lines afterwards, because DAT lines should always come at the end of an LMC program. Going to put an initial value because we are straight away saving a value to these memory addresses. Okay, and like I say, the main approach here is to subtract num2 from num1 repeatedly and count how many times that is being done. And once num1 becomes less than 0, that's a sign that we can stop this repetition. So we need to have a count. We need to keep track of how many times we're able to do this. That's going to be our output eventually. And we need to, subtract num2 from num1. Well, currently, what is in my accumulator at this point? Well, currently num2 is in the accumulator here. So therefore, I need to load back in num1, and then I can sub num2 from it. And then effectively, we're going to keep doing this while we have a positive result. Once it drops down to be negative, it means we've gone too far and we need to stop the division. So we could, at this stage, kind of just initially put in our loop. We're going to keep repeating until it eventually becomes negative, at which point we can output the count, and then I can stop. But sadly, it's not going to be quite that simple, because right now we're not taking into account the count at all. We're not actually adding anything to the count, which is the difficult bit. So if I do 12 div 5, that should give me 2, but we're going to get nothing because I didn't actually change the count. Okay, so we've got some work to do in this area of my program. We need to first of all kind of save the current value of num1 again, because num1 is what's being subtracted from. If it was 12 div 5, well, num1 starts at 12, then after the first iteration it becomes 7, then it becomes 2, and so on. And well, actually at that point it should stop because it'd be negative the next time it goes round. So I need to save that to memory, because I need to also, at this point, load in the current value of count. I then need to add 1 to this current value of count. Then I need to save this value back to memory. This is just me adding 1 to count. Bit of a faff to have to do in assembly code, as we are used to. Because I've set 1 as a label, I need to make sure I then at the bottom actually assign that to be the actual value 1. So if you're doing this on a computer, you've got the luxury of then trying your code as you go. I appreciate that in an exam situation, you can't do that. In an exam, you're just doing your best ultimately, but you can run through your code and check it. Now I'm testing it here, and that's not a great sign that it's iterating for a long time and nothing's being shown. So there must be an error somewhere in this code. Well, we only get output when it eventually becomes negative. So that maybe explains why I've not got output here. Something's not quite working in this loop part. And one thing I can see straight away is actually I forgot to set count to be a value. Count does need to start somewhere. Let's try it starting as 0, but I think that might need to change in a minute. And could try that. I'm not convinced that's going to fully fix it. I think one issue here is let's stop that before it crashes. I'm looping back to this line here where I'm then subtracting num2 again. But what is it I'm actually subtracting that from? What is in the accumulator at that point? Well, I would say it's the value of count that's in the accumulator at that point. So what I need to do is I need to make sure that we are also loading back in num1 at that stage, because it's really num1 we care about. It's not count that I need to subtract from. I'm subtracting num2 from num1. Let's try this with the same example, but that's still not giving me the output I want. I think the issue there is, again, I need to really be thinking about what is in the accumulator at any given point. And here, BRP, we're branching to see, is the value in the accumulator positive, in which case branch. But again, it's not the count I care about, it's num1. So actually, let me undo what I just did, put the loop label back there. And we need to also make sure it's here that I'm loading in num1, because it's num1 I'm seeing if it's positive or not and deciding whether to loop or not. So what is that? Third time lucky, fourth time lucky? Let's see where we're at. I'm not convinced we're going to get a perfect answer here. We should get some output eventually. There we go, few. So 12 div 5, is it equal to 3? No. 5 goes into 12 2 whole times, not 3 whole times. Let's try another example just to see if we can get some more data on this. Let's do maybe 15 div 3, which should be 5. Are we going to get 6? Is it always going to be 1 extra than what I've got here? Looks like it may well be. So the issue here potentially is that we are adding 1 before we are checking whether it's a positive value or not, which means we're adding 1 no matter what. And so the count is always going to be 1 extra than it perhaps should be. Now I could try and move all of my add 1 codes further up my loop, but I'm not sure that's going to be the most quick way to solve this. I think just simply setting count to -1 initially means that it's not going to overcompensate here and add 1 even if it doesn't need to divide. So for example, 10 div 10 should be 1. We would have got 2 if I hadn't made that change, because it was always adding 1 when it shouldn't have done in that case. If I do say 5 div 10, this should be 0. That maybe better explains why that was an issue, because we were adding 1 before I got the chance to check whether it was positive or not. So making it -1 means I'm still doing that check before I do the branching operation, but at least it's not adding an extra 1 no matter what. So that should be my final answer there, or is a final answer. It's not the only way of doing it, but is a working way of doing it. Completely appreciate that in an exam situation, it's a lot harder to do. If you are doing it on a computer, you're able to do what I did and try things out and play around with it a little bit. When you're doing it on paper, do it in pencil so you can rub stuff out. The only way of checking whether you are right or not is just to slowly go through your program, pick some example inputs and see if it seems to be working. That is hard to do in an exam situation, so not worth stressing about too much. Just try and do your best